This presentation, title generated by ChatGPT, Evolving Excellence, Refining Your Robot Through Iteration. I'm basically going to talk about probably what I would consider one of the most important skills to have in FRC, which is learning how to iterate. And the reason I say that is because you can apply iteration to like anything. So it's really easy to just make the blanket statement that it's like super important because you can use it anywhere. So my name is Greg Bilodeau. I am a solutions architect at Ionic. I help companies make apps. I basically mentor corporations to use my product. I am Woody Finalist Award winner in 2020 during COVID. So I got to celebrate at home, which if you know me, that's like the best place. Doing that in front of everybody would have been traumatic. I was a student on 930 from 2007 to 2010. I'm old. I mentored the team as a college student for 4 years, and then in 2015, my lead mentor had to step down, and somehow I ended up with the team, and so that's been there. So this is my 18th season of FRC. And the robot's in front of this, but I've built a lot of robots, and so I figured a good start to the iteration presentation is how my life has iterated with robots. So I started in 2007, and that robot is made out of plywood. Somehow it made it to finals. We were the third robot, and that year, our alliance could do nothing during the entire game until the end game. That's the only thing our whole alliance could only participate in the end game, and somehow we made it to finals, and somehow we only lost by 1 point. That robot was in pieces by the end of the finals. 2008, we built a robot that was literally just 2 wheels. Took us the entire season to build a robot that was 2 wheels. We somehow ended up as an alliance captain, had done no scouting whatsoever, and were very confused. That's cool. 2009, you're going to be able to tell which robots we don't care about because the pictures are terrible. 2009 existed. This is a terrible year. But that was the first year we built an offensive robot, and it was supposed to shoot game pieces, and I think it shot 2 game pieces the entire season. 2010, after being scared by being bad at offensive robots, we built a defensive robot again, and this was a year where we played soccer, and we made a goalie. It had a little pneumatic shield that went up and down. Yeah, that's all I'm going to say about it. Those were my 4 years as a student. We basically built robots that couldn't do anything. 2011, the year after I graduated, they're like, we're going to build a cool arm, and we're gonna build an offense robot again. I'm going to talk a little bit about because I think it's an important topic to broach, the concept of mentor-built components. 2011 here, a mentor designed this arm, and they did the math wrong. And what they thought was a foot, it was going to extend at 1 foot per second. They forgot to convert it to feet from inches, and it actually went 1 inch a second. And that's very, very slow. And I'm not dissing on mentor built here, but I think it's important to point out because there's a lot of misconceptions here. And so here's one instance where it did not go super well. That robot did well though, but not because of me. 2012 basketball year, we decided, I don't know if any of you, rookies especially won't be, but even if this is your senior year, anyone familiar with window motors, snowblower motors? Yeah, we decided that would be a good intake motor and a good bring the ball from the ground to the shooter motor. So it took 10 seconds for the ball to go here to here. And about half the time, these were foam balls, about half the time it would rip the skin off the ball before it got to the top. It was great, it did not work. But it was a shooter, and we could shoot to the top of the Panther Arena if we put it at full speed. That doesn't equate to points at all. 2013, Frisbee year. This is the first year ever we won a robot award. And none of you were in the presentation except maybe the 4 people because you were all in here. But if you heard Brian and Abby speak, Brian won a robot award. Okay, he was the programmer on the team that year, and using an Xbox Connect as a vision sensor was the coolest thing back then. We had an actual laptop suspended in the middle of that robot. And so we won the Innovation and Control Award that year. Brian won the Innovation and Control Award that year. Speaking of robots we don't care about, 2014 was terrible. We decided to do a shifting gearbox because we heard shifters were cool. And you can't see it here, but we decided to put Mecanum wheels on that shifter. And so all of the benefits of shifting were gone. And the thing was trash. And as some foreshadowing here, it was also a catapult, which was a really bad idea. 2015, we built a robot that played the wrong game. It was meant for the game that it was there, but it was the wrong robot. And if you heard my previous presentation, the first step, the most important thing is building the right robot. This was not it. You were supposed to, you know the gray totes you get in the kit of parts, this was the year where you stacked them as a game piece. And we decided to be really cool if you picked up two at once. It wasn't cool. 2016 was kind of, so those four there were my college years. And then I took the team over here and I got really, really excited about leading a team and wanted to push us really hard. And I pushed us in the wrong direction. 2016, I'm like, okay, we're gonna sit back and actually think about things. And this robot was, actually one of my favorite ones. It's hard to tell because bumpers cover half of it, but it's a really pretty robot. It's powder coated blue like this one, and our school colors are blue and gold. And I found some yellow pneumatic wheels, and I found some yellow PVC, and so it was very thematic and awesome. It won an award, and this one I actually feel like wasn't just Brian, so that was cool. And you also notice in 2015 we transitioned to sheet metal design. I'll talk a little bit about that. 2017 here. So 2007 we made it to finals. From here until here, we never got out of the quarterfinals again. 2017 we made it to the finals again. This was the year that taught me about iteration. This is the year where I realized how important it is. Because this year, this robot is essentially 2-3 pieces of sheet metal for the entire thing. You can see here, this is one giant piece. Every mechanism on this robot was attached to this piece. And the CAD for the balls was wrong. And we didn't measure. And so we got this entire robot assembled and realized that the CAD had the balls at 5 inches, but they were 5 inches nominal. They were really like 4 3/4 inches. And so nothing on this robot touched a game piece because everything was too big. And so we had to redesign half this robot, but everything was attached to these plates. And so we had to redesign the entire robot to add 1/4 inch of spacing to everything. And so we moved away from this sheet metal design pretty quickly because of that. 2018, this is my favorite robot. Maybe this one here is now my favorite, but this year was really good. Elevator, loved it. 2019, this was our most successful robot. It's literally just the 2018 robot, but playing the 2019 game because the games were so similar. 2020, the year that didn't happen. I'll call this 2020 year kind of our overconfidence year. 2019, we got really successful. In 2020, I'm like, we can do that again. It did not work. And I was so happy when COVID killed that season. So when I foreshadowed about catapults here, 2022, we built a catapult. I built a catapult. 2022, coming off of COVID season, our team lacked a lot of experience, and so I stepped in a lot more than I had ever. So going back to this mentor build thing, I stepped in and I actually designed about 80% of this robot so that our team could function while our CAD kids learned. Our CAD kids followed behind and designed the same robot again after me to kind of learn, and we ended up building that robot afterwards as the robot that competed. But when I said foreshadow the catapults are terrible, catapults are still terrible. And so there's a big slide in this presentation about this, but after our first competition, we designed a whole new robot, which you can't really see here. Alan, would you mind trying to figure out the light switches again for me? But this catapult got ripped out and we designed a whole new robot with a whole shooter, intake system, everything in 2 weeks. Iteration. And then this last year, this robot, I like this robot too a lot. But it took me so many years to kind of understand the importance of iteration, the importance of trying something, failing or succeeding, learning from it, and taking those things that you learned and applying them to making it better. Okay? And that doesn't just apply to robot design. That applies to programming. That applies to strategy. That applies to how you structure your team meetings. Learning from what worked and what hasn't to make something better, make your team better, is key here. So what is iteration? Some dictionary, a fundamental concept that refers to the process of repeating a set of instructions or operations until a specific condition is met. In the context of FRC, refining and improving a robot's performance through continuous analysis and improvement during every part of the season. Just trying new things, what works, what doesn't, keeping what works, and making it better. So this statement here, I'm sure if you've been around FRC a while, or if you just went to my last presentation, you've heard this statement. There's no such thing as good enough in FRC. I'm gonna be real here for a moment. How many of you look at this and just kind of get a little bit of anxiety? Like I look at this and I get anxiety. I look at this and it's depressing, right? It means you're never good enough. It means you're never done. It means no matter what you're doing, you're always gonna be doing more. And so the main focus of this presentation is going to be explaining how you use and approach iteration to ignore this statement, okay? To basically stop looking at your robots as they're never good enough and start looking at them as what do they need to do today. So this statement, no such thing as good enough, only applies if you look at like the entire FRC season as a singular data point. I portrayed it as like a bar graph here, where you've got your goal, and then you've got where your robot is, and there's this big gap of what it's missing, and that missing is just depressing. It's just stressful. I put anxiety-inducing, all of this stuff. Like, this is what leads to burnout on everybody. It's just always picturing things as not good enough. My robot sucks. My robot can't score a game piece yet, and it's week 4. My robot doesn't have an autonomous yet, and we go to competition tomorrow. All of this stuff are feel bad moments. Robot performance, I put it here, needs to be evaluated as an infinite series of moments. So instead of looking at it as a bar graph of pass fail, is my robot good? You need to look at it as, am I achieving my goal for today? And as long as those goals progressively get you to the point that you need to get at, you can frame your robot's progress, your own progress, in a more positive way. So I spent so much time on this stupid graph, making it in Google Drives. You know, the line's pretty and everything, but blue line there is like where our robot is, gold. Red line is the goal there for that moment. And if you become a programmer in industry, and this may be true for other industries, I'm not positive, but they have this concept of the inverse here is like a burn down chart. It's making your requirements over time until you reach your goal. So the key here is there's 100% a reason at any point on this line to call your robot good enough for that day, okay? Right here, we're good enough. We did it. Hooray, we did it. Right here, okay, we have a little bit of work to do, but it's this little gap. It's not looking at this point up here. Every day or every meeting, you need to be evaluating, and I'm not saying you need to get out a piece of paper and time yourself and all this kind of stuff, but framing it, thinking about it, your robot's performance, and determine what changes are going to be the most impactful right now. What is most important for you to finish? This will mean, and I'm sorry the robot's covering up the bottom there, this will mean that at some point, you're gonna be done with parts of your robot because there are other aspects of your robot that are more important. I think this is most applicable and also most frustrating for the line between when is my robot done mechanically and when is my robot done programmatically, okay? I am a programmer day to day, but my focus on the team is mechanical design. And you always want to make it better. You always want to be tweaking it. You always want to be making it lighter, stronger. Programming needs that robot. You need to understand when you're done today, when you're done for now, so that if programming has the most impactful changes now, you need to do it. You need to let them So I came up with these, I gave them the same letter, so they're all like alliteration. I have 3 stages of iterating here. So I have resolving, refining, and refactoring. What I call resolving is basically making sure your robot works, right? Iterating to find the weak points on it, iterating it until it can play 50 matches without you needing serious maintenance. Iterating on it to make sure that it actually picks up that game piece. Okay. I've got a picture, 2 pictures here. This is of this arm, actually. This picture on the left is 2 weeks or a week before our first event. We'd gone to Sussex, it went well, and then we went to MRA for their event. And about halfway through the day, the arm sheared itself and fell off and was irreparably broken. And so we were like, we'd only played probably an event or an event and a half's matches on that robot, and it was broken to a point where it would not function for a decent amount of time in that state. And we cannot have that happen during a competition. So we redesigned things. Unfortunately, all the redesigns were really internal to this piece right here, which is this black piece in the middle. But we redesigned it until that point, and we never had a failure like this one. Again, we did have some failures with our carbon fiber tube at our first event, where we were using too thin of tube and it sheared. It actually the tube actually tore in half. It was really cool. But we were ready for it. We had a bunch of these tubes already made because we knew that we hadn't invested enough time in resolving this tube and understanding how it's going to fail. Iterating to refine. This one's the most fun for me and probably for a lot of you guys. Making it go faster, making it better. Taking a working feature and speeding it up or adding another step to improve its performance. This is super exciting and super fun because, like, as people, we like it when, in this case, when numbers go down. We like to see progress. We like to see, oh, we shaved off a quarter second on our scoring. Oh, we shaved off a second on our autonomous. Oh, we added another step to our autonomous mode. Now it works great and amazing. We've done all this, but our drivers never touch the controls. Our driver doesn't know how to deal with a robot that moves this fast. I had these pictures in the previous slide, but this was our robot before it went to Sussex. This was our robot before it went to our first event, Midwest. And this was our robot before it went to Wisconsin. We basically doubled the time each, or halved the time it took to score each time. This one here, if we'd done this week 1, or if we'd done this for Sussex, we would have fallen on our faces so much. Because it took an experienced driver who knew our robot to drive this. Because if they were driving full speed, when that went up, we just fell on our face. We did that test. The first thing we did after seeing this is we had our driver just full speed slam, like he was going to score, start bringing the arm up and stop. You know, when you want to score as fast as you can and just throw it, just fell right on its face. If we'd had that here, it would have been over. But this is really fun. This is my favorite part of the season. And then iterating to refactor. So there are going to be times when the initial strategy that you have chosen on is incorrect. It's a bit of a rough way to phrase it, but the concept where no amount of improvement to that design is going to make it surpass a better approach. So I've got 2 examples here. This left one is from this season. This left picture was our original intake design. It was horizontal wheels, a more classical intake design, honestly. You see this for a lot of seasons. The problem was if you didn't hit those cubes dead on, if you hit it a little off, the cube got flung away from your robot. And now you're chasing game pieces around. The last thing you want your driver to have to do is chase game pieces. You want to be able to, the concept of touch it, own it, where as soon as your robot touches that game piece, it's yours. This did not satisfy that. In this case, as all of you know, we saw a wild stands intake and we were like, a better use of our resources. Bringing it back to the previous presentation, a better use of our resources at that time is just taking the design that we knew worked and working on that, building that, allowing us to use our other resources, the rest of our team, to further our robot in different ways. Okay, it's not like we're copy pasting and then just all sitting in the chair going, yay, our robot's done. No, it's we copy pasted this so that the rest of our team could work on the fact that there's like a giant steel bar here, or our team could work on the fact that this print needs to be strengthened, or our elevator's got a lot of friction on it, all this other stuff. Our team was applied elsewhere. They were doing other stuff. On the right here is the 2019 season. I have a GIF of this one later on in the presentation, but these, you had to pick up these giant, like, I don't know, like this big discs. And they had Velcro on the edges and you slapped them against a wall. And you had to pick them up in this orientation too. And so we had a design, we actually had a couple designs. This is one I had a picture of where we had rollers here that would actually grip the top and bottom. We just didn't like it that much. About week 2 or 3 of the season, we saw some videos of teams. This design here is actually what was used in, if you go back even further, I'm starting to date myself here because you guys probably all your first game, the oldest of you was probably 2020. I think 1, 2, 3, yeah, 2020. So like 2015, you had to pick up recycling bins that had these lids with a hole in the center. And a lot of teams would drop down this. It looked like a cone, drop it straight down into the hole, and then open it up, and then they could just lift up, and it was attached. We saw that, and we turned it horizontal, and just shoved it in the hole, and went boop, and now it was ours. There was like 40 pounds of pressure holding this disc. Nothing could rip it from us. And it could be sideways, it could be cocked, and it was in our robot. So, refactoring, the idea of like going back to the drawing board. So these are your 3 bits of iteration. I put this funny graphic here, the life cycle. Really it says that you're always doing all 3. You're never going to be like stopped on one piece. How you balance these 3 though, it kind of determines the consistency in your success from year to year. Because like I said, it's really, really fun to spend all your time making it go faster, 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 but maybe it's the wrong design. And faster, faster, faster is still way slower than high tide over in California, just like zip zop zooping across the field and scoring 30 game pieces when you score 2. This slide doesn't translate well in low light, but I tried to break it up to like where you're focusing during the season. So this green circle here, during the build season, you're really just focusing on making your robot work and making sure that you have the right robot for the competition. It's not important that it goes super fast as long as you know that you have room to make it go fast. Okay, and what this means and how this applies is like, you know mechanically it can do the thing, you run it at low speeds so that you don't break everything while you're still learning, but you know that you can speed it up. And that's this refining. Early competition season, really you should be then focusing on fixing things that happen during matches, right? Like driving your robot at home is entirely different than driving it against 5 other robots under pressure, where your driver suddenly forgets how to stop before they slam into a wall, all that kind of stuff. So you're going to need to find how to fix it. And then at this point, you want to start making it go faster, right? Now you're trying to win competitions. Now it matters how fast you go. And in the red here, I've got 2 circles. I've got a solid one here, because during the end of the season, you're just trying to score more points. Like the whole goal, your robot should be working consistently enough, or you understand how it's going to break and you have plans for it. But at this point, you're just making it go faster. You're making it score more points. I put a dotted line here around refactoring because the opportunities for refactoring are there, and there's 2 of them. There's one where you're like us in 2022 and realize after your first competition that, oops, you designed the wrong robot. You don't want to be like this, but you're having to refactor a whole half of your robot. Or, and there's what you want to strive for more, is that you're refactoring because you've seen another team do something that's really clever, really smart, and really easy, and you know how to implement that on your robot. In this case, and I'll talk about it in the slide, that was our ground intake here. we were constantly refactoring that throughout the competition season. We talked about it in the previous presentation, but that ground intake changed between every one of our competitions because we were watching the growth of this game and how it changed and how it flowed. So, kind of restating what I just did here, the priorities for the different parts of the season. So during your build season, your biggest priority is making sure you have the right robot, making sure that you design the right thing for your team, meets your goals, scores well, assuming that's one of your goals, and that it has room for improvement as the season progresses. Usually, like I said, this just translates into speeding it up, like in programming, saying, I'm going 10% speed now, I want to get it to 60% speed. It may also be just swapping a gear ratio real quick if you're using a planetary gearbox. Your next priority is making sure it doesn't break, right? And I mean, really, really early on in the build season, like you want it to last more than 30 seconds, so that's your higher priority. But as you approach like week 4 and 5, you just want to make sure it lasts a decent amount of time. And then I have here under resolving that autonomous mode runs consistently, but doesn't need to score well yet. What that means, it sounds more daunting than it is. What it means is if you have an autonomous mode that drives 5 feet forward, that it does the same thing every time. I'm not saying that it consistently scores 3 game pieces. I'm just saying that your programming, basically the tuning that you've done to it, to make sure it goes the same distance each time. And we'll talk a lot about autonomous in the latter half here. Holy cow, I got to speed up. All right, and then refining, tune enough to move your iterations forward. Basically, you want to make sure that you're not wasting your time on here, but you want to make it go fast enough that you can improve on your refactoring to understand, like, do you need to refactor? So how do you find that correct robot? Fail fast, research, copy, verify your concepts quickly. We talked about this in the previous presentation. We use a lot of masonite, so we can laser it out. It's basically cardboard. You can see it down here. There's a cardboard gearbox that we did, so we can test fit and flow. This robot right here, most of the scoring parts in this robot are all masonite. The elevator gearbox is this one right here. The scoring mechanism was cardboard. The electrical panel was all cardboard. Half of this robot was cardboard, and we were doing driver practice on it. And this is how our driver got really good this year. You can see what I was talking about before with this piece.
Do you have a machine that cuts the cardboard?
We have a laser cutter. The school has one. And those are a nice investment. Honestly, those are probably the first like big piece of machinery I would grab these days, because you can, technically if you have good ventilation, you can do polycarb on it, but it gets really stinky, and some teams do. That laser for the cardboard, oops, it's great. You saw that. And then, where is it here? Plan for short-lived proof of concepts that verify the important questions. I had this GIF earlier, but you can see obviously the robot ends up failing about at the end of this GIF because of the cardboard, but it got the value we needed out of it. We needed to know how the driver was going to pick up those cubes and if it was going to work or not. We didn't need to know if the top half of that robot could be held up by metal. That didn't matter at this moment. Don't get attached to designs, or you'll end up rebuilding half your robot after your first week. You can see a bigger picture here. Like the entire part here got entirely redone. This went from a catapult to a hooded shooter in 2 weeks. And we basically lost at least one competition to this. Like we go to 3 competitions these days. Our second competition was wasted almost because we had not figured out the nuances of this new design yet. Your first event, you should be making sure that it really does work for the full competition. Now you really want to start refining your scoring capabilities, making it score faster, making it score better. And then, like I said, still, don't overdo it here. You want to make sure that you're refining just enough for success at your next event, okay? Because all of this takes resources, and everybody has finite resources. There's no reason to make it be more successful than it needs to be, because you're going to be you're spending your resources somewhere else, or you're not able to spend as many resources if you dedicated them all here. Juggling so many priorities It's really easy to do the fun one, you just need to make sure you're conscious of that. And then refactoring. At this point, when you go to multiple competitions, I want you guys to be thinking about refactoring, okay? It's a low priority here, but the biggest benefit to going to 2 competitions today in the no bag era is that you can make changes, and you should be. Your robot should be evolving throughout the entire season. You don't show up to your week 1 competition and say, this is the robot for the next 6 weeks of competition. No, this is the robot for this week. By the time I get to Wisco in week 4, it should be better than it is today, because we've learned. You can apply that learning. So please, don't waste your multiple competitions. That is the biggest benefit to going to more than one. Reining in your refinement. So keeping your robot working through a competition is essential, but your top priority is likely winning a competition, and that should be your first priority there. So at this point, you're bouncing between speed that robot up and breaking the things that broke because you sped it up. Making things go faster is dangerous, things break. You gotta find that balance. You do not want to speed things up so much that your robot breaks and suddenly it's the day before competition and you have a broken robot, and now you're worse off than you were. An example of this, so find it good enough for the next event. In 2023, yes, Tara?
Do you usually build 2 robots to your prototype robot, or?
We used to.
Yeah.
These days, we end up with like 1.5 robots,
Yeah.
where the practice robot gets cannibalized for the real robot. And that was the case this year. So at the end, programming had a drive base left that they could use, but not a whole robot. So find the good enough for your next event. In 2023, we showed up to our first event with a single autonomous mode because we knew the top team at the event. We knew what they were going to have, and we wanted to compliment them because we knew we were not going to be the top team at that event. We wanted to be pickable, and I'll dive into that soon. So I showed this before, just showing your refinement. You know, things get 2 times faster every week. I'm not going to hover on that slide much. So then finally, your iteration priorities for like the end of your competition season, in this case, champs. I like this, higher, further, faster. At this point, your robot, you're just trying to make it score more points. That's your goal, score more points. Usually this means making it go faster, but this can also include some refactoring based on what you've seen. So like I said, this ground intake changed every competition because we understood the game better and wanted to copy what we'd seen, or copy strategies that we'd seen. In this case, it was making our ground intake faster. It didn't happen until champs. We tried every competition. Actually, we showed up with this at Wisconsin, and we ran it during practice day, and I had a coach of another team. I don't think I told you guys. Maybe I told Abby. I had a coach of another team come up to me because we had won our first event, so we were already qualified for champs. They saw us practicing with this, and they said, "Are you guys actually gonna try here? Or are you just like phoning it in at this point?" And I'm like, bruh, it's practice day. Like, let us try things, but no, we're gonna bring it our all. So that was a funny little bit. All right, so how to iterate. I've got this funny graph where I talked about before. Iteration can be a destructive process. You can be breaking things down to build up new things, but you need to plan. You need to look forward because you don't want to end up like you're in this process here. You don't want to suddenly, your competition comes and you're down here on one of these divots, right? Because you broke too much and couldn't put it back together in time, and that happens. So this, if you don't do any forward thinking, if you just go in with a hammer and a saw and just start breaking things apart to rebuild it, you have a lot of risk here. You need to, what I put in here, filter your progress. You need to plan, you need to think ahead. Aggressively limit the scope of your changes as the season progresses. You shouldn't be making huge destructive changes 3 days before your competition unless it absolutely is required. If your robot is like, oops, I have been staring at the 2012 game manual when I should have been staring at the 2013 game manual, oh gosh, okay, fine. Watch the competition to see what you missed. It's very common when you show up with the same robot at a week 6 event that you did at a week 1 event to not realize that the field got stronger. Week 1 events are easy because everybody is at the same, like, oh man, our robot was just finished yesterday. Week 6, they're not like that anymore. They've had 6 weeks of refinement. You need to make sure you have 6 weeks of refinement. So watching the competition to see what they've learned and done. Only iterate enough to get the information or results you need. Again, don't waste a lot of time iterating on a masonite side panel to add lightning holes, because that doesn't matter. Okay? Iterate enough so that you can move to the next step. And then don't overcomplicate every step. It's really easy to, again, like add lightning holes to your masonite, or to think that this next bit needs to, like if my autonomous mode, if I need to suddenly add a 3-piece auto, but also I need to speed up the other pieces, and I'm going to destroy my entire autonomous mode so that I can get here, don't do that. Prioritize your changes, but take calculated risks. Just understand the effects of what you're doing, okay? If I'm going to make a new intake out of the pieces of my old intake, that means that you're not going to have an intake for a while. And how does that affect the rest of your team? Does that affect programming? Do they have to pause what they're doing? Were they doing autonomous modes before, but now they can't because they can't pick up a game piece? Prioritize your changes, think about how it affects, but still take those calculated risks. And then use the tools you have available to you, CAD, simulation, or great examples. You can do a lot of iteration in CAD. You can do a lot of iteration in simulation for your programming, where you don't have to have a robot in front of you to do that. Okay, so autonomous modes. I love this one. So our first competition was week 2, Midwest. And here is what we knew end of February, so about 2 weeks before the event started. We knew, one, that the top team was going to be Wild Stang. And we also knew that we were, not exactly close. Like, there's a lot of competition all fighting to be Wild Stang's best friend. And then, like, February 26th, Wild Stang posts this video, which, of course, is not going to autoplay with the sticker. So I'm going to come over here. They post this video of their autonomous mode. February 26th, like 3 weeks before their first event. And suddenly, they've got an almost working 3-piece auto before week 2. Like, they missed that cone, they were close. We were nowhere near that point. We didn't have a robot that drove at that point, really. It was kind of there, but it kind of wasn't. So, but we wanted to be with them. And you know how this game worked. You couldn't have 2 robots both playing on this side. So what we did is our autonomous focus was on this side, where there's that bump. And so we, 3 days before competition, start to finish, did this auto. We are on the red side in the bottom right here. And we weren't focused on speed, we were just focused on consistency in the area where they weren't. And so we drive nice and slow, we go over the bump, we scored that 1 piece, we pick up a second, and we very slowly, like ironically, oh, it skipped a slide. Well, there's the end result, either way. The other slide was just not us with Wild Stang. Or I did it wrong. Either way. We made that one autonomous mode for Midwest. That was it. Because we knew it would complement Wild Stang, and we got picked because of it. But our next event was Wisco, and we knew that wouldn't fly at Wisco. We were coming in with a regional win, and we were coming in looking to be the favorite. Just speaking numbers here. And that autonomous wasn't going to work anymore. Like, 1 game piece is nothing. So we then started working on our 3-piece auto. I believe we're blue. Yeah, we're blue and we're up here. And it was worse than Wild Stang's was 3 weeks before. We never nailed the 3. You see, we pushed that game piece there. But because we had a regional win, we could take some risks. Now, I know I just said that we weren't phoning it into that one guy, but we were taking risks because of our position. And I want you guys to also be looking at what risks you can take. And because we did this, of course it's going to autoplay again. Don't want that. At our next event in Pittsburgh, this was, you'll notice, Quals match 5. So the very first event, or first match of the day, we are in red right here. And we pick up and score all 3 of those game pieces because we invested the time at Wisco. That being said, like at Wisco, it wasn't like we had the worst autonomous there. We didn't interfere with our partners. We just took more risks than we would have normally if we were coming in under a different circumstance. So this is a good example of iterating with autonomous, and a good example of how I don't know how to use PowerPoint. Um, Here is some examples of how we iterated with carriage design. So this past year, I think in like October, Rev announced their Max Spline. This guy right here, right, and all their ecosystem for it, all this cool stuff. And so in December, we started just playing with it, like in CAD. Like, what is it going to look like? And one of the things we played with was an elevator carriage with an arm on it. Ironically, that turned out to be like this game. I don't have any insights into what the games are each year, so this was just pure luck. We always make guesses. Like this year, right now, we're designing a turret with herringbone gears because we're anticipating a shooter. But if it's not a shooter, all that time, I mean, it's not wasted, but it is. And this is what we did this year. We looked at this, and so this was like version 1. Just some practice with figuring out how this Max Spline works because it's kind of funky. Like we don't have something like it. So then we started designing some carriages. They got real funky. Like this one, just belt to belt to belt to belt to random sprocket that doesn't need to be there. All this. We were like really looking at 254's carriages where they get so crazy and cool and awesome. Like I want to do that. So this was V2 where there was like no bearings on it whatsoever. V3, I'm like, okay, that's too many belts. Or sorry, V4, that's too many belts. And so all this was before kickoff. You can see, I mean, this is actually kind of finished, surprisingly. But, you know, like we just have sprockets floating everywhere. And this one doesn't even have shafts. We saw the game get announced. And so we were like, wow, that actually works. We came back and we took this. And so the first design we had post kickoff was this guy right here. And so we do a lot of our iteration, just like if we're just talking about pure iteration now, we do a lot of it in CAD to start with because you can understand a lot. Unfortunately, the lighting in here is kind of upsetting, but this first version is actually pretty similar to what we ended up with, but instead of, what we ended up with was a chain drive to move this Max Spline. In this first version, we had gears. And so we took that, we looked at it, kind of talked about it a little bit and realized that like the forces that single tooth of gear is going to see when this arm is flying around is probably more than we want to risk. We never actually made this one. This one was just in CAD. So a couple changes later, we made this one. And this is like, there's no pictures of me at all. I hide from the camera, but I found this one of me, and so I had to put it in here. And so we made this one, which it's hard to see, but you can see it right here. So there's a gearbox behind this wall that goes to a chain that drives right here. And this is the same thing over here. So we switched to a chain drive. And we made this one, and as you can see, it's actually made out of masonite. This one went on the robot. This one moved up and down. This one lasted for quite a while, honestly. We ended up making it out of polycarbonate because we liked it, so we replaced it. We should have made it out of aluminum, but we didn't know that. And this design lasted until like a week before competition. And then we were using those max 90-degree gearboxes, right? Those were super cool. Those also sold out like 3 days into the build season and never came back. We had 4, and in our robot design at the time was 4. So we had no spares. And at MRA, the gears started stripping on them. We're like, oh, okay. That's not good. Same thing as the arm. Like the arm brake was the last thing that happened, but we were spending half the day fixing the gear stripping, and when we finally were like, okay, this is good enough, the arm then fell off, which was super, super cool. So then we had the next design, which we removed the max 90 gearboxes because 1, there was none in stock, and so we had no spares. But 2, like, I think it's funny. The first design, we were concerned about the gear teeth, and then we didn't think about that at all with the max 90, and that ended up happening. So we removed that, made it all sideways here. This is actually what competed for the entire build season, or the entire competition season. It had a critical flaw because we designed it out of plastic. The only things that held this whole thing together was these. There's a 0.75 round tube here, and there's one down here. And they had 2 quarter 20 bolts on each plate. In the plastic, they started to crack like crazy, and we had to replace these plates 3 times? 2 times. We had 3 sets. 2 times. Luckily, maybe unluckily, the final one was after champs. It was for IRI. So during the competition season, we had to do it once. This also had an issue where there's a lot of slop in this arm. Like, I'm not moving the gearbox at all, and I can move this. I might be moving the gearbox. No, I'm not. Yeah, no, this is all just slop in the chain, where it can move good like 15 degrees on its own. And that translates to the arm kind of doing this as you drive around. So we had another design. I don't have CAD of it, but it's hard to see here, but it was a custom cycloidal gearbox. And those things are ridiculous, and I don't understand them. And they basically just like vibrate in place and it spins, and it has essentially 0 backlash. But we finished it 1 week before champs. So we had a big team meeting about this actually, because we had 1 week and we had a couple things we wanted to do. We wanted to make the ground intake better. Like, we knew that was a good thing. We also didn't really like the slung. We deemed it too risky to put on because of the opportunity cost of losing the ground intake, because that would just hit the stop. Because all of our resources would go into this, because it's programming, it's mechanical, it's design, it's fabrication, all into this into 1 week. We had to refactor our code, we had to retune all of our positions. So it got built, it's sitting in our shop, it's really fun to play with because it's like no backlash. You can force it to move and then it moves really smoothly, but it's super cool. And we get to use, and we probably won't have a use case for it again. So luckily, I didn't finish. I got to this point when I was making this. I'm like, I'll make a nice transition from that to the end. But we only have 2 minutes left, so I think I thought this through really well. Am I correct that we only have 2 minutes left? Does somebody have the schedule?
Yes.
Okay, just making sure. So kind of to summarize here, iteration is the main driver of your success during the season, okay? Not just iterating on design, but iterating on your match play, iterating on your competitions, iterating on your strategy. Being able to go to a competition, being able to drive your robot, see what worked, what didn't, and then acting on those observations, making changes and making it better. That is what defines consistent success. I know I started this presentation talking about like mentor build and stuff with a little notes there. There was gonna be more, but I realized I spent way too much time on that slide, and that's okay. A lot of teams will look, I know when I was a student, I looked at Wildstang and I hated them. Okay, I looked at them and I'm like, that Raul Olivar, his fingerless gloves as he drive coaches and works on the robot, and Big Al over there, that big mean inspector who makes everybody else illegal but lets them do whatever they want, and I hated them because I thought that Big Al and Raul, the other drive coach, was running their entire team and doing everything for them and making it work. That's not the case. Not the case with Wildstang. It took me a long time to understand that. It took me being in a position where I was watching our team succeed and flounder to understand. And so the real secret behind success is being able to look at your robot and team honestly and make changes and grow that robot over time. You don't want to show up to your week 6 competition with what your robot was 6 weeks ago. Okay, that's 12. We have 10 minutes before the next presentation. I am giving the next presentation, so I will be in here. If you have questions, very happy to answer them. But thank you guys so much for being an attentive audience. I'm sorry this one went a little faster because I ran out of time, but that's okay.